Welcome to the first proper part of the quantum video series. We'll be looking at a lot of different complex topics and trying to take them one at a time. Before we get started though, here's a quick look at a timeline, just to get a sense of understanding of the context of all of these discoveries. We'll be going almost perfectly chronologically, with the exception of the hydrogen atom, which we'll recap at the very end. This quest for understanding has been going on for hundreds of years, and to ignore that would be to minimize it. The very first point of interest in this situation is light. Light is a form of energy that can be found all around us. It can be generated through a transformation or conversion from another energy form, such as electrical or chemical energy, or within a combustion process. For example, the sun produces light energy through nuclear fusion within its core. Our perception of light has to change from something shiny to something that can travel across space and is vital to our understanding of physics. A man named Hooke first connected wave properties to light in 1665. He was investigating microorganisms, visualizing them, and discovered a pulse of light. It seemed perpendicular to the direction of the movement of light, a transverse wave. Then, in 1690, Huygens described it mathematically, while Young was proving it with an early iteration of the double slit experiment in 1801. Wave behavior was exhibited as the two beams of light appeared to interfere in the same way that two physical waves would, creating a distinct and expected pattern: interference. Then came Faraday, whose experiments began to link electricity, magnetism, light, and other forms of radiations. Maxwell's equations of 1864 unified and concretely. It began with the theory that any change in a magnetic field can then create an electric field, such as this equation shows, where the electric field multiplied by the infinitesimal element of a closed loop is equal to the change in magnetic flux divided by the change in time. This proved that electromagnetic disturbances aren't transmitted instantaneously, but travel through space as waves at a finite speed. By calculating this and finding that it is equivalent to the speed of light, light was assimilated with the electromagnetic spectrum. After consistent increases in clarity and the development of new physics theories that further support the wave properties of light, suddenly, an issue during an investigation into the relationship between ultraviolet light and a black body. A black body does not naturally occur. It is an object that absorbs all radiation coming its way without a singular ray reflected. Instead, it's re-emitted. The previous theory suggests that the warmer the body in question, the higher the peak frequency. Using the most prevalent theory of the time, namely the Rayleigh-Jeans law, infinite energy would be reached despite the conservation of energy. Therefore, this must be wrong, sending classical physicists spiraling, because it didn't just impact the subatomic world, but all reactions involving thermal emissions. This was one of the key errors of physics at the time. Quantities were expected to be infinitely divisible, that matter could always be further broken down, and that matter could vibrate with any quantity of energy. The savior in all of this? Max Planck. The year is 1900, and he suggests something novel: the concept of discrete packets called quanta, the lowest unit that a form of energy could be divided into. He then also calculated the vibration of a particle. This is the famous letter h, Planck's constant. There's two main equations that we use for this. E equals Fh, where the energy is equal to the frequency of light multiplied by the Planck constant. This is derived from the E1 minus E2 equals hv equation, where the E1 to E2 represents the oscillator transitioning from a higher to a lower energy. E is the resultant of that, which is also known as the quantum radiation, which is proportional to the frequency times Planck constant. The graph here shows that the change in wavelength frequency as the intensity of the radiation increases. As can be seen, Rayleigh-Jeans law goes far beyond Planck's, with a potential to continue infinitely. Planck's reaches a peak and slows down in its increase from there onwards. Both laws are applicable to a lower frequency. Rayleigh-Jeans' understanding was not as much erroneous as incomplete. Then came Einstein. To say he is a visionary is to undermine all of physics as we know it. He was in agreement with Planck in respect to the energy packet theories, and further developed the theory in regard to the unit of energy of light specifically, naming these energy packets photons. He would then also develop Hertz's theories regarding the photoelectric effect. The experiment in question is simple: a beam of light is cast upon a metal, and the electrons emitted are observed as they are deflected into a nearby collector, which will experience a current due to the movement of this negative charge. The energy of light was thought to be dependent on the intensity, which we perceive as brightness. Therefore, a brighter light should knock electrons off more easily, regardless of color, which is dependent on the frequency. Any light should eventually cause electrons to be ejected. This is supported by wave theory. However, this is where classical physics no longer holds up. If the light's frequency was too low, regardless of the intensity, no electrons would be ejected. Meanwhile, electrons would immediately come off in response to high-frequency light, regardless of the intensity. This demonstrated that the ejection of electrons was dependent on frequency, not the intensity, and therefore that light delivers energy in discrete packets, not as a continuous wave. This effect can be visualized in the following three equations. First off, we know that E is equal to Planck's constant times the frequency, and then we can format this into different equations and equate it to the work function of the metal and the kinetic energy of the photoelectron, which is just a specific word for an electron released due to light being shot at it. We can substitute the formal equation for kinetic energy, which is half times mv squared, where m is the mass of the photoelectron and v is its velocity. Within this equation, Planck's constant cannot change the energy. Only the frequency can. When the no photon collides with an electron, if the frequency isn't great enough, then the electron will not be released. This is the threshold frequency, the smallest frequency needed for electrons to be released from the surface of a metal via radiation. The amplitude of the electromagnetic wave is also relevant. It is proportional to the number of photons hitting the metal's surface. The Compton effect is a phenomenon that focuses on the scattering of high-energy photons, usually X-rays, due to collisions with electrons. When a photon and particle collide, the particle would increase in speed as the kinetic energy increases. The photon will experience the photon wavelength increasing. The photon is a part of an electromagnetic wave. Different wavelengths, which represent the distance between two identical points along a wave, are equivalent to different sections on the electromagnetic spectrum. For example, gamma, it is transported by multiple photons of a high energy level but short wavelength, while radio waves are a smaller collection of photons of a lower energy level and a longer wavelength. In the diagram of the experiment, there are 4 steps. First off, within the X-ray tube, there is a cathode which generates 3 electrons which are aimed towards the anode. Then the photons will hit the Perspex disk at a specific wavelength, resulting in their scattering. These scattered photons are then measured by the spectrometer at different angles, 0, 60, and 120 degrees. The energy of photons changes based on the angle of scattering. There is an observed shift in the wavelength, which promotes the theory of particles, not waves. Electrons were believed to be stationary before the collisions, and that they gain kinetic energy through the photoelectric phenomenon. In the Compton effect, unlike the photoelectric effect, where photons are completely absorbed, the photon scatters off the electron, losing energy and increasing in wavelength while the electron gains kinetic energy. If each scattered X-ray photon were to interact with only one electron, the following formula would be applicable. This proves particle properties as it would require light to flow in a particle-light stream. Overall, this shows that depending on circumstances, light can behave as both a particle and wave, because it has both a wavelength and frequency, which are inversely proportional. It is the frequency, not the intensity, that will affect an electron. Planck's theory dictates that energy isn't continuous but quantized, and quantum theory is built on this. Some theories state that everything, including space and time, is quantized. There is a limit to these divisions. Light cannot be divided further than photons, a composition with which Einstein agrees. So far, we've seen that light is a quantum particle. But what about matter? Are these quantum behaviors hiding somewhere within atoms? The answer is yes. According to classical straightforward-ish physics, electrons in orbit around the nucleus should release energy and eventually lose it, therefore no longer resisting the electrostatic force and falling into the nucleus, crashing. If that was true, our world and matter would look entirely different. When hydrogen is excited by things such as electricity, it doesn't emit the continuous energy expected, but rather specific lines of color. This proved that atoms are quantized systems, not continuous ones. Therefore, he proposed that electrons reside in distinct energy levels called orbits, and that they may move between them. Bohr devised the atomic model that we study in school, but it's Schrödinger's model that we'll visit in the next video, which furthers our understanding within the world of physics. Although it beautifully explains some things like spectral lines, it has its limitations, such as the fact that it couldn't explain more complex atoms. It was one of the best ideas of its time and movement in physics. To further our knowledge and understanding, we're approaching a whole different complexity, which we'll further break down together soon. Thank you for joining me. I look forward to seeing you in the next video, where we'll start out with de Broglie's matter waves. As always, drop any topic recommendations in the form below and questions in the comments. I hope you've enjoyed enough to like and subscribe. Stay tuned for the next video. Have a wonderful day.